Hey everyone, welcome to the third video where we will discuss the syllabus for week 3. I'm hoping that you have completed the syllabus for week 1 and week 2. So now we are getting to the part of deep learning and the world of neural networks. So we will start with a very basic definition of what a neuron is, and by neuron I mean the artificial neuron, and a comparison that we generally draw with biological neurons. Just take it as an inspiration. Nothing. Don't try to go philosophical in the fact that we're trying to replicate what the brain does and all that stuff. Just take it as a fact, as a pinch of salt, that it was just a set of inspiration and nothing more than that. So we go to neuron structure. We talk about what a neural network is in definition, right? Because yet we are not aware of the mathematics. Then we discuss about what a perceptron is. We talk about multi-layered perceptrons, we talk about weight matrices, and we talk about hidden layers. 7 hidden layers. Just kidding. So we are talking about the ways in which these single neurons are connected, how they form a network, and associated with every connection out there is a weight associated with it. So and a corresponding weight matrix between every layer. What is the meaning of hidden layers? How many layers you can put in between the input layer and the output layer of a neural network? We get to the concepts of gradients, learning rates, saddle points, local and global minima. So brushing up your calculus will be very important, your partial derivatives and stuff, because when you're talking about neural networks, concepts like forward propagation and back propagation, they require concepts like chain rule. So it would be good if you just brush all the stuff up. Then we have gradient descent and stochastic gradient descent, and then we have the concept of activation functions, vanishing gradient problems. So again, as I said, that you have an algorithm, there will be ideal scenarios, there will be scenarios where the algorithm goofs up. So a sort of goofing up is vanishing gradient problem. So you'll need to study that. Then we have parameters versus hyperparameters of a network. So there are certain things that a network learns, right? And now I'll talk about why the word book slipped up out of my mind. So for example, let's say you are preparing for an exam. So there are certain parameters that you choose and there are certain parameters that you learn. So which book you want to learn from is a subjective question, right? Like let's say you had an option of 10 books and you selected one to prepare for your exam, and how much you learn from that is something that depends on your capability of how well you can learn. Similarly, in networks, we have a certain set of predefined choices that we can make. Those are not learned during the training. Those are something that you have started with. Okay, so let's say you have a neural network and you have decided to start with 7 hidden layers in between. So that 7 is something that you have already defined. That is not something that is the network will learn. Okay, right? And similarly, in contrast, that would be an irony. In contrast, you have the weight matrices, and individual weights are something that your network is going to learn when the model is being trained. So now we come to the part of weight initialization techniques. There are a bunch of techniques that you have, which are written in the next few points: random initialization, symmetric initialization, Xavier and Glodot initialization. Again, these are very important concepts for your interviews. I'll provide links for articles that I've written on them. Then you have your counterplots, batch normalization. Just batch normalization and all that stuff is to make your learning process faster and better. Optimizers. Again, when you are training a model, your algorithm can get into some problems, some blockers, I'd say. So there are ways in which you can optimize your compute resources, optimize the way your algorithm learns about and updates the weights. So there are different optimizers available out there. You have momentum, you have NAG, you have ADA delta, you have ADAGRAD, you have RMS prop, and you have Adam. Adam is the most common optimizer that we use and very common in interviews. Then we have concepts like softmax in multi-class classification. So softmax is something that is related to the final output layer. Now this was for the artificial neural networks. Now we get to the part where when we are taking images, operating on images. Hence, we are coming to the part of convolutional neural networks. So you need to understand what a CNN architecture looks like, what is feature extraction, different layers used in a CNN. We will be looking at concepts like channels, padding, strides, filters, kernels, max, minimum, average, pooling. So whenever you're talking about CNN, it's very easy to make projects now. And the code part is never difficult, but in interviews, these are like one word, like one-liner questions. They're very common. What is filter? What is a kernel? What is max and minimum pooling? And all that stuff. Once you're done with that, you will take up the topic of transfer learning, residual connections, residual networks, image segmentations. So in images, you have a variety of problem scenarios, right? Either you just want the classification, whether there is a dog, is this a dog or a cat? In a second, the second possibility where you want to find out, you want to just draw a bounding box around it. The third one, you need to have a higher level of accuracy. That is like you want to segment it. You just for example, you have background removers, right? In images, you have like a nice selfie and you just don't want the background out there. So you go to online tools, you use Adobe, and you remove the background. So that is an example of image segmentation. So once you're done with that, object detection, brief discussion on GANs, because this is a syllabus more for the beginners, generative adversarial networks. I have seen that the mathematics of GANs generally strike fear in people. Then we get to RNNs. So now we are coming from image data to something that is having sequential information like text, like song, or basically anything that is that has inherent sequential information. So you come to the problem of vanishing gradients in sequential information. Let's say we are operating on a large paragraph. You'll get to know what once you read about it. We will be talking about sharing weights, a comparison drawn with CNN. We will be talking about LSTMs, GRUs, gates. So again, as I said, please pardon if this is not making a lot of sense because I cannot provide detailed videos. Again, I'll try to provide articles. Encoder-decoder models, context vector, bidirectional networks. Blue score is again like a metric that you have. Disadvantages of one hot bag of words model, space efficiency. So if you remember that in week 2 we did a minor introduction to NLP, things like stop words, bag of words and all that stuff, TF, IDF. Now again, the classical read about something, then read about what are the disadvantages about that, and then move on to the next theory, the cycle of life. Then you go to a semantic relation of words. So words have relations with each other. So for example, let's say I say that apple, and along with I say mango and Tata Motors. Okay, so obviously it's closer to some a fruit rather than an industry. So again, there is some sort of sense required with that. By apple, I didn't mean the industrial company apple, but the fruit. So how to model all these information, these confusions that you might say as of now into numbers. Next, we come to representation of words as vectors, word embeddings. So we started with something as bag of words. Now we're getting into embeddings. There are ways in which you can make these embeddings. Word-to-vec model. We have continuous bag of words. We have skipgram. Then we talk about embedding matrix in the continuation. Glove vectors. Now we get into something that is again getting you to a bridge that is acting as a bridge between your classical encoder-decoder models and the upcoming transformer models that are state of the art. So you're starting with attention mechanism. Then you are going with the details of attention, local and global attention. Then something that I feel that you should not try to cover up in week 3. I think point number is 43. I think starting after 40. So 41, 42, 43, 44, 45. Transformer architecture, self-attention, QKV matrices, query key value, multi-head attention, masking, BERTs, GPTs. If you want to take time, definitely feel free to take these into your 4th week. There's no pressure in that. You're just getting started, and I think it would be better if you're comfortable that you take this course to like 1 month duration. Like, so this neural network thing you can take over 2 weeks, and if you're more comfortable with that. So I think we are done with the syllabus. I'll try to provide a Google Drive link to this entire documentation, and if you have any queries, please do post in the comments, and maybe in the future I'll come up with a syllabus which is now, instead of being theoretical, be more focused on the practical aspects. So again, as a conclusion, this was for 3 weeks. There might be a few things that I've missed up. There might be some things that I missed, and there are a lot of things that I missed deliberately, because it was a 3-week course, and now you're having 4 years B.Tech focusing on AI. So see you soon in the next video. Bye bye. Thank you.